This is Lean Together 2025, and our next speaker is Siddhartha Gadgil, who's going to tell us about real-world auto-formalization.
Yeah, thank you very much. Thanks to the organization for this opportunity to speak. So I gave a slightly grandiose title, Real-World Autoformalization. Maybe I should say pragmatic autoformalization, that is focused on not a measure of how well it works, but how useful it is. I mean, whether it's useful or not, of course, is for all of you to judge. But that's the goal, I mean, to try to be useful. Sorry, I have, this thing is blocking. So autoformalization is just translation of natural language mathematics to lean code by AI. I forgot to say that. It's the auto part. We all do formalization. And it can help with formalization, human formalization at two levels, interactively. And when you're doing it interactively, it has two ways of helping. With a beginner, it will help with lean syntax, somebody who really doesn't know lean at all. But even, say, an intermediate user like me, we don't know how something is formalized in MATLAB. So it might help in as a sort of search for terminology. And also in the spirit of the lean MATLAB port, eventually, I mean, it's not yet there in this thing, where we had a first syn port, Mario Carnero's code generated broken MATLAB 4, and that was manually fixed. So similarly, a draft translation might help. In this case, in fact, you can get draft translation where a language model can be asked to fill in more details as well from the original proof. They're good at that. They're good at filling in details as well. And the other goal of auto-formalization in the whole math AI business is to provide a bridge between natural language reasoning of the usual foundation models, which has become really good, and lean, or the appropriate interactive theorem prover. As far as I'm concerned, it's lean, and anyway, this is lean together. And the role of lean in this case would be, one, to ensure correctness. Until a few months or even a few weeks ago, I would have said that's the crucial thing, because language models get things wrong all the time. But in fact, they've become much better at getting things correct. But the second role of lean is having a modular organization of mathematics with abstraction boundaries. Many of you would have seen the Johan Komala, Adam Topa's article on this. And there is also a Jeremy Avigard article on a similar issue. If you're doing mathematics on a large scale, even if you have a small probability locally of error, your probability essentially one of error globally, unless you have something to stop this from happening. So it's the organizational role as well as just correctness checking role that you expect lean to play. So these are complementary to each other. LeanAide is the system that I'm developing. It's not just me, but the main developer, and it is open sourced. AI/ML is deeply integrated with this, and it helps both with better auto-formalization, we'll see how, and hopefully with usability in Lean. Okay. I'm focused on tools and workflows, and the tools are available at all stages, even if they have plenty of rough edges now. In some cases, barely working, some cases working reasonably. And iteratively, I keep trying to find minimum working examples and improving this. I feel this is better than benchmarks, partly because benchmarks are just very expensive. If you want to run things on a AI system, minimum working examples are more illuminating often, and certainly not so expensive. And so ideally, you would want Lean and AI to complement each other, and the system to be usable by people who are not experts in Lean or experts in AI. If you're experts in one of them, that's a bonus. Maybe initially people who have some knowledge of both, but minimum knowledge. Okay. So in the spirit of this talk, I'll see our first demo. A very big disclaimer here. I have not cherry-picked or rigged the responses. However, I cache the responses. This is for two reasons. One is there is, of course, a cost to every time you query things. And secondly, if you keep asking the same question to a language model, you get different answers. So debugging the next stage becomes horrible. So responses are cached. As a result of this, you'll see things happening very fast. And in fact, they take several seconds in practice. And that's one of the things really to work on. Okay, so now let me go to here. I hope you can see a VS Code window now.
Yes, we can.
Okay. So here is an idea which is as in hash lean search and hash Moogle and hash Loogle, but originally from Sagredo. You end with a full stop to prevent things from being triggered again and again. You end with a full stop. So here is syntax for a theorem. I'm calling this theorem silly. Both the name and the colon are optional, and it's a natural language statement instead. Okay. Now, when I do put a full stop here, this has gone through a process which we will see. Now it was fast because of caching, but the process involves query to a language model, some post-processing, etc. And this gives you a try code action. Okay. So here we have got our theorem. It ends with a sorry proof. Okay. Now again, another example. There are infinitely many odd numbers. In this case, I omitted the name. Well, in this, it auto generates a name. You can also use this code action to get the result. Okay. So this is the latter, I think. So as I was trying to say, this is of course useful for a beginner, but not just for a beginner, because I would not know, for example, that it's module.rank. I still don't know if this is the best formalization. I mean, there is a whole algebraic hierarchy. The dot notation helps a lot, but in this kind of formalization, you have to really search MATLAB to find the correct terminology. Okay, so this was the first tool that I wanted to show in action. I'll tell you the performance of it. I feel it's good enough to be useful already, but there's a lot of improvement. Okay, tool 2 / doc. This I think many of us would like to use. Well, it's kind of boring to write documentation, so let's get a doc string automatically added by the system. Okay. So this was my second example of this. And we'll come to how this all works. And the third one will make more sense later on, but I have put it in this file, so I will show it to you. This is, as I said, a focus on a workflow, and my hope is that in the future, a mathematician is simply going to be working with a Lean VS Code or the Lean server or something, one environment. You don't have to switch contexts. There are often requests on this. So this ask is simply asking the language model. There's no Lean involved here at all. I mean, it does use, of course, the Lean's system calls to use curl, etc., but nothing really Lean specific, just to avoid breaking the workflow. And here we get an answer and a query and response. Okay, so let's me invoke the code action. Well, what it did with the code action, another thing which will make more sense a little bit later, is it gave me a text. What is this hash text? Well, this is a new Lean command, and some little bit of markdown. It tells you what the query was and the response was. You could implement a chat protocol with a hash chat and so on. That's completely elementary to do this. When I come to the later part, the context in this context it doesn't make so much sense, but it will make a little more sense in another context. But as I said, the point is that you don't want to interrupt your workflow. You want to just keep working, and you formalize something, or you load a file, you query an LLM, etc., and keep working with a mixture of informal and formal. Ideally, you should be calling interactive automated theorem provers as well. Okay, so let me get back to my slides. Yeah. So what happened in this? Well, so this is not a new model. I'm using GPT-4o. I'm not working on tuning models. My collaborators did try fine tuning, but these days it looks like just using the best models with prompting and post-processing works better than trying to make a better model, at least for my level of skill, or even a little beyond my level of skill. Okay, so how do we prompt? We are given the statement of a theorem. We find, say, 20 documentation string in MATLAB, okay, that are closest to the statements. And closest here is specific OpenAI embeddings, and include them as examples. And then we query GPT-4o currently, but this is configurable. You can use a local model, which you host yourself. You can, as long as you have the URL, you can ask anything. We query this with 10 responses and ask for, say, 10 responses. And then we post-process, and crucially, we discard responses that are not valid Lean code. We do not parse. So if it does not parse, it's discarded. If it does not elaborate, also it is discarded. And in fact, One of the relatively recent improvements is we have two elaboration filters. We elaborate it as a type. We also build a command, example colon so and so colon equals by sorry, and elaborate that as a command, and both should work. Only then it's accepted. Okay. Now, some technical issue is that language models are chatty, and however much you tell them, they will sometimes make a few comments and then include it in a code block, etc. So we cannot simply only elaborate the whole thing. We'll have to search and elaborate within it. We also do some mild auto corrections. These things have been changing with time. And another slightly fancy thing we do, but it has hardly any effect currently in what we have seen. But as things get complex, hopefully it would. So, well, we have many responses. Maybe we had asked for 10 responses, maybe 7 of them were valid. Okay, but we don't want to just take the first response. There is a greedy option which takes the first response, as it was in the demo. Instead, what we do is we group them together as being equal, not just syntactically equal, not just definitionally equal, but if AESOP can prove one is equivalent to the other. And this is AESOP with some configuration. AESOP is using ring and LeanAide and omega. Okay, so a little bit of a power tactic if it can prove. Okay, this is a slightly obsolete example. The syntax keeps changing, but I'll come to the, but it gives the essence of what is going on. So we start right on top. We have a system prompt, which says some instructions. And then we give it some pretend example. So the user said this, and the assistant replied with this. And then the user says something else, and assistant replies. And then finally, the user says something, and assistant, what do you say? Okay, this is the basis for giving this example. So here is the translation to Lean. If a vector space is two-dimensional, then it's finite dimensional. We saw this. So this is a silly statement. One of my ideas that I like is coming up with these examples. They're little misleading in the sense they tend to be rather easy statements, so they're easier to translate. But there is no risk of contamination. Rest assured, there will be no text in which you will have this theorem proved that if something is two-dimensional, it is finite dimensional. Okay, forget about formalizing it in Lean. So, but in addition, we had 40 theorems. There was some contamination, and then some false statements, again to guard against contamination. Initially, when we were using codecs, false statements were good for a test. As the models got better with the false statements, sometimes they would just say the statement is false instead of formalizing it. Then we excluded it from our data, but we also included some cases where the translation was wrong, but it seemed to be correcting the statement. So anyway, they're good. So we had a success rate of about 85% in our thing, but maybe these examples were a bit easier. It's hovering around 50% in the Putnam bench. I'm working on pushing this number up. I feel this is still useful because, well, some little change has to be made to the code because you can post facto edit. If there are small mistakes in your translation, you can post facto edit. Okay, but we want to push this up. First thing, this was done a while ago, is there weren't enough doc strings as good examples. So found that problem was this. So we created more data by informalization. So it's the other way around. We saw that with the hash doc. That is, given a formal theorem, proof, or code, you describe it in natural language. So what I did is I took a heuristic. If something appears in at least 3 theorems, and then to my surprise, some things like infinitely many primes were hardly used at all. There are multiple statements of that. So if something already had a doc string, so there were 2 criteria of being important enough. If it was important enough, we informalized it. Okay. Now, informalization is different from formalization. We did not give examples because, again, a lot of these things you have to think about how you would do it as a person. When a person will always find it easy to translate from a language they know well, they don't know well, to a language they know well. And these things know English very well. They're translating to English. They don't know Lean particularly well. So, and what you have to give them is a sort of dictionary of the language they don't know well. So we include the definitions in the statement of the theorem. We don't bother to give examples. And the results were good. I mean, this is not measured. Okay. So actually there were 2 versions, an original version, and after I posted it, there were comments about it being too long. So a cut size version. And in addition to that, now Lean Search or Mathlib Search and Moogle both have APIs. So you can also search for examples from Lean Search and Moogle. And so there are 5 sources, the docstrings, the 2 informalizations, Lean Search and Moogle, and these are blended together. I mean, time will tell what blend is good. I would have liked to use just Lean Search and Moogle because that would get rid of a lot of dependencies. But unfortunately, so far the results are not good using only those. Some other comments about trying to improve the translation. So one thing we do is perform round trips. Now you could perform round trip in both directions. And one of them was start with a lean statement and that's implemented. You informalize and reformalize and see if the two are, say, ASOP equivalent. This is good for benchmarking, but not useful in translation. So for translation, I do it the other way. I translate to lean and then back translate and then ask a reasoning model. We ask O1 Mini whether the 2 statements are the same or not. Okay. This is good both to evaluate because it's usually correct. It rarely gives claims something is correct or wrong incorrectly. But also to filter, because say we have 7 things that elaborate correctly, we did our majority voting and so on, but we are, instead of picking our first choice, we can pick our first choice that passes a round trip. So this improves the quality. And then, as I said, we try to understand what things are failing and improve them. One of them is just a definition is missing. And we have experimented. It's not incorporated in the main code. There's all the helpers are there. We get a language model to generate the definition, translate this and include it in the prompt. And then this improves the translation. Sometimes even when the definition is present, it doesn't pick it up. Either the definition is in MATLAB or even in the statement. So you are getting extract and include in the prompt. Then some things it has logical problem. Language models today have logical problems. Perhaps in a few months these will go away. But greatest odd divisor, it either hallucinates a term or somehow makes a hash of it. You get the model itself to rewrite it as the greatest number, which is odd, and which is a divisor of so and so, and then it starts translating correctly. So there are this is just various steps to improve things, going a little bit ahead. And then sometimes you just do meta programming, like this exists unique. If you have exist unique x, y as natural numbers, this is banned because it's ambiguous. But usually the meaning is there exists unique x, there exists unique y. So I simply have meta programming which rewrites it. So it's rejected by the elaborator, but you just rewrite it. Okay, so this was really at a sentence level. What about at a larger scale? At a larger scale, this is really very rudimentary code. So I'm really showing it just to make things tangible. Let's say, how will things look when the world improves? And hopefully it's a matter of weeks and months, not an enormous time before things start getting better. So when I have an iterative formalization, the idea is that you can start with various sources. You can start with just a problem, ask LLM to prove it, and that's what I'll illustrate. And it gives a theorem and proof. Now you don't directly translate it, you translate it into a structured JSON text. Then you do the autoformalization to get a lean code and elaborate. And then you try to use rule-based tactics to finish the proof. Okay, so this is a well-known method. Draft, sketch, and proof is maybe the first paper which had this. By now, the idea is that you decompose, and even mathematicians do it this way. We don't give logical proofs. We break it into enough pieces, and the final thing is supposed to be just algorithmic. Okay, so we generate a text. This is translated and used to this. Okay, so a language model is used to translate text to a JSON format with detailed instructions. Okay, so there'll be a type. There are detailed instructions. In fact, there's lean code which generates the instructions as well as parallel Python code which does this. And then we translate theorems into statements using our statement translation after picking up the entire context. Okay, and then we have to do some meta programming to remove variables, etc. Okay, so assertions within a proof become have tactic, and then it goes to ASOP. And following an idea of Eric Wieser, we search for have a fallback to sorry as well. Okay, so let me get to this. So this was my translate demo. Okay, here's a, oh, sorry, I didn't want this. Oops. Okay, so here's the demo statement. So this is code really meant for experimentation and development. So it's not user ready. That's why it dumps a lot of stuff. So I'll show you what is going on in this example. This is from a few days ago. There are some improvements, but hopefully there'll be big improvements over the next even just 2 weeks here. So suppose we have the product of two successive numbers is even. So I start with a program, I write lake exe code gen and have product of two successive natural numbers is even. I just give this question. This is the proof given by GPT-4o. Okay, it splits it into two cases. Okay, then I get a language model. It was again GPT-4o with detailed instructions to make things in JSON. Okay, I chose JSON because language models know JSON. From what I hear in some places, maybe XML will be better. I don't know. We'll have to keep experimenting with this. So it generates it. There's a theorem. It says the status is proved, and there are proofs. There are cases, and so on. And then it generates the code. Okay, I did not use the auto naming. I'll use the auto naming in the future here. And some things, this is a little tactic which says hash note. There's also command hash note just to throw in comments in smoothly. So it split the thing into bicases. It had the positive and negative case. And in this case, it actually proved the result. Because you see, even though it did not prove some of the lemmas, I'll come back to where the lemmas fail. It didn't use them in the final proof. So here we split into case, here we have an auto, and both cases were actually proved. So in this case, the code generation worked fully, but let's see where it failed. Well, here I was slightly surprised Aesop couldn't do it, but that's because I don't know all the details, but one factor is we want to show n is 2 into k, but even is r plus r or k plus k, which is not, of course, identical expression, is different enough to trouble lean in this case. Okay. The other thing is just a little mistake. So what we want to do is not just have an assertion, we want to have a k and a property. That code is written. Unfortunately, if I do that, then Aesop starts running out of time, max thread. So there's work to be done on that. And then these things are a little bit of a mistake. This should not be for all k. It should use the k here. Okay. Already this n is used here, but a similar thing has to be to k. Okay. So this is the status. The hope is that we can keep building on this and actually just generate code, starting with a document. And I think this is a reasonable start and doing it in these two steps. Okay, so just one more tactic to say here, and before is there's a tactic called why. So why asks a language model why this is true, and I want to point out one thing. Okay, in this why, we begin by, you notice it says to prove this theorem, we begin by considering the definition of even number. According to this definition, natural number is even if there exists r such that n equals r plus r. The thing is, it was smart because we fed it definition. So this is the point about using AI. You have to prompt it and give it information. So just like I did in informalization, when I have the why tactic, it not only gives the statement, but it actually looks at the definitions that were used in the statement, in this case even, looks up the definition of even and gives that. So that's why this outline has a better chance of working, and iteratively we would want to auto formalize this and so on. Okay, and again, if I click here, this is a little tactic called proof, which does nothing so far, but in a future iteration, it will give you a code action which will offer to iteratively formalize this following the other tactic. Okay, so this was the one working and one sort of working thing. I mean, one more just to make things tangible, as I said. With that, I should just say I should thank my collaborators. In phase one, Anand is the only one who's actually helped me with lean meta programming. The others have, but Naveen Goyal was the one from whom I learned all these things can be possible. He's at Microsoft Research Bangalore. So for the first year or so, this was a group, and then we disbanded. Everyone vanished. Last couple of months, there's a group of young collaborators I have, and they have helped me quite a lot in the later stages. And crucially, I mean, you need resources. So Microsoft was generous enough to give me a grant under their Accelerating Foundation Model Research Program, and that was crucial for a lot of this. And Google gave me research credits before that. Okay, some just hopes of plans. I should fix the code generation. I'll do it. Improve translation at sentence and proof level. And again, I said pragmatic. So part of user experience is not just workflow, but installation. So installation is not as good as it should be. It's now working though. As of yesterday or so, it's working. If you choose a stable toolchain, you can use it in a third party. The translation is very slow then. I have to diagnose that and fix it. Okay, tasks and prompts to auto formalize at a larger scale. So here we are looking at a theorem and a proof. If you are looking at a full document, you would want to first break it up into pieces, formalize piece by piece, but in the context of a later piece, include a summary of the previous part, at least the theorems and definitions and so on. So this is relatively straightforward work, but it takes work to do all this. And the other final goal is that currently Lean is really used to formalize things we have already discovered. The hope is that Lean, especially with these embedded AI calls, will be used by mathematicians for discovery as well. So there you need to conjecture things, you need to experiment, etc., etc. So you will need commands to state something which you don't know whether it's true or not. Nothing difficult about this. Lean provides a lovely API to do all this. And I believe the the Magma project did include such commands. And I think other projects have also done it. So that's all the way. Okay. So with that, thank you all. I stop.